Hello students, welcome to the lecture number 2 on the chemical equilibrium. In this lecture we are going to discuss the dynamic nature of the equilibrium. In the previous lecture we have discussed about the basics of the equilibrium, what is basically chemical equilibrium is, what is the general characteristics of this chemical and the physical process that we have discussed. Now in this video we will going to discuss the dynamism of the chemical equilibrium. So you can write today's dynamic nature of equilibrium. When this is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. When the reaction, that is a reversible reaction, reached the equilibrium, at that time the concentration of the reactant and the product become constant, and we will call the mixture of the reactant and product at the time of equilibrium, we call it a reaction. When the reaction has reached to its equilibrium state, the concentration of the reactant and product become constant, and with the time there will be no change of this concentration, and it looks like that reaction has stopped. It may be wrongly perceived that reaction has stopped, but this is not the case. The actual thing is that there is the equal rate of the reverse and the forward reactions, and that is why the composition of the equilibrium mixture become fixed, become constant. And this can be experimentally demonstrated by using the Haber's process of synthesis of ammonia. In this process, the equation will be like this. For the equilibrium, you have to put this sign that we have already discussed in our previous video, that is called states about the reversibility of this reaction, and this is the reaction, and you will have to put this gas, and hydrogen is also a gas, and produced product is gas. However, in the synthesis of the ammonia had taken the known amount of dihydrogen and dinitrogen, and it has been put in a concealed container for the reaction to proceed under high pressure and high temperature, and intermittently able to measure the amount of ammonia produced, and also he able to measure the unreacted ammonia, unreacted dinitrogen and dihydrogen. And what he observed, after some times the concentration of this ammonia, concentration of the hydrogen and concentration of the nitrogen become fixed, means that reaction has achieved its equilibrium state. And you can see from this graph also, From this graph, you can easily understand. Initially, when time t is equal to 0, then the concentration of dihydrogen and dinitrogen is the maximum, but there is no ammonia present there. And with the time, when the reaction has started, you can see easily that concentration of this hydrogen, dihydrogen, goes on decreasing, concentration of nitrogen goes on decreasing, but ammonia, concentration of ammonia goes on increasing. And you can see at that point the concentration of hydrogen, concentration of nitrogen and concentration of ammonia become fixed, become constant. That means this reaction has achieved its equilibrium state. Now what he has done, instead of hydrogen, he has taken deuterium. Deuterium is another isotope of the hydrogen. He has taken the deuterium, the D2, and with the same operating condition and the same temperature and same partial pressures of the gases, he has again conducted the study, conducted this reaction, and he has continued this reaction, allowed to continue the reaction to achieve the equilibrium phase. And what he found, after some time, when the equilibrium has achieved, the same amount of ammonia is produced, but at that time the difference is that ammonia is here ND3 instead of NH3 in the previous case. Now what he has done, that for the two reactions, this is one reaction and second reaction, we get thus N2 plus 3D2. When he has used that deuterium, the isotope of hydrogen, and what he has done, he mixed this two reaction mixture. Two reaction mixture he has mixed, and this has been continued for some time till it attains the equilibrium. When the equilibrium is attained, then this reaction mixture, when the resulting reaction mixture from these two reaction mixture, he analyze these species present in at the time of equilibrium, what it is constituent by the mass spectrometer. By mass spectrometer, he has analyzed these contents after the mixing of the two reaction mixtures, coming from this reaction and coming from this reaction. And what he observed? He observed that there is the ammonia is present. Ammonia is present along with the deuterium content ammonia is present also. He observed in this case that NH3, NDH2, ND2H and ND3. These all the species he observed in this equilibrium mixture at the time of equilibrium, and also he observed the hydrogen. Hydrogen is this, and here he observed hydrogen with deuterium and with this hydrogen and deuterium. So all these species he observed. So what it signifies? It signifies one thing, that during after the equilibrium, after the equilibrium the reaction is still going on, and that is why the hydrogen and deuterium atom has been scrambled out from their places, and it will give a formation of this type of product. And this is only possible when the reaction after the equilibrium still continues. So these isotopes is possible, the mixing of the isotopes is possible due to this fact that after the equilibrium, when the equilibrium is reached, there is the reaction, that is a forward reaction and backward reaction still progresses. The reaction is not stopped at all, but due to the equal speed of the reverse reaction and the forward reaction, the equilibrium composition become constant for the time. So we can understand this. Another very important thing that we need to understand, that this reaction, that is this reaction, the equilibrium state we can achieve by taking the hydrogen and nitrogen. Also, we can achieve the reaction by taking the reverse direction. So in both the cases we can achieve the equilibrium if we take the reverse reaction, and also we can take the forward reaction, and both the cases we will achieve the equilibrium. Now we can have another example of the reaction, that is this hydrogen and iodine, hydrogen gas and iodine gas. This is another example of the reaction. You can see that when we take equal amount of the hydrogen and iodine gas, it will produce the HI, hydrogen iodide. And in this case, if we make a plot, this is the time, and here that we can see the hydrogen gas, hydrogen or iodine gas, with the time this is the concentration. On the y-axis we have shown the concentration, in the x-axis is the time. As the reaction progresses, the concentration of hydrogen and iodine goes on decreasing, and the concentration of hydrogen iodide goes on increasing, and the time will come then the concentration of this hydrogen iodine and hydrogen iodide become fixed, and this is called the equilibrium point. And now what we can see, what we want to see, that this equilibrium state we can also achieve from the reverse direction also. This is the reverse direction here. Now in this case, that we are going from this direction, and this reaction in this case is hydrogen iodide, taking hydrogen iodide as a initial material, and in that time you can see hydrogen iodide at the initial time having the highest concentration, and it goes on decreasing with the time, and it comes at the same equilibrium point. It takes the same equilibrium point when we start from the reverse direction, that from the hydrogen iodide, taking the hydrogen iodide, and it has been decomposes to hydrogen and iodine, and you can observe one thing, that this equilibrium point has been reached in the same way that when we start with the hydrogen and iodine. And if we take the same volume, the number of hydrogen and iodine atom is same, then the equilibrium mixture, the concentration of the equilibrium mixture will be same, whether we start from the forward directions, from the hydrogen iodine, or we can start from the hydrogen iodide. So this case we will observe the equilibrium can be achieved from both the directions. So in this lecture we understand the very important thing in the equilibrium, that equilibrium is dynamic in nature, but after the equilibrium has been achieved, then the reaction is still on the way, on the process, but it is at the same rate. And we can also see the equilibrium can be achieved from both the directions, from the forward directions if we start from the forward direction, and if we start from the backward directions. And the equilibrium mixture, the concentration of the equilibrium mixture will be same if we take the same number of atoms of the constituents, and it will give the same concentration of the reaction mixture at the equilibrium. So that is all for today's video, and this video we have understood about all this important thing. Okay, thank you very much for watching. If you like this video, you can share with your friends. Thank you.